Thank you so much for coming to the Global AI Night tonight, and thank you for joining my talk. My name is Lucía, and I'm going to be talking about the research I've been doing for my master's thesis in computer science, which has been about automatically anonymizing videos using computer vision. So, as you all know, privacy and anonymity have been kind of like hot topics in the tech industry recently, and especially in Europe because of the approval of the GDPR, which I guess everyone is kind of familiar with, thanks to these lovely accept cookies notifications that we all get in every single website. And this project actually started due to the GDPR. It started as a project for the Past Pop Music Festival, which takes place here in the Netherlands. And what they basically want is, so they have all these CCTV cameras in the surroundings of the festival area, and they would like to be able to store these recordings so that in the long term they could analyze, for instance, patterns in pedestrians and in the traffic, so that they can improve their logistics in things like crowd control, access control to the festival, etc. But right now they are not able to store these videos because the GDPR says that, as long as you're not a, let's say, public institution, you cannot store videos containing personal data. But you could if you can ensure that they are completely anonymized. So this is where the research question came in. Is it possible to completely anonymize a video, and how could we do that? There have been several methods proposed for this, both in research and in the industry, in academia and the industry. I think the most known one is to use image filters to process certain areas in the image frames in a video, especially faces. So, for instance, we can use blurring filters, pixelating, masking. The problem with this is that, in this case, faces are not the only area in an image that can contain personal data. So then another intuitive approach would be to use these same filters, but apply to, let's say, the whole area in the image that corresponds to a human body. The problem of this is that there have been several studies where it was proved that we as humans are able to still recognize people even through these filters. So if recognition is still possible, GDPR still applies. Another approach has been to use some kind of key or SID to encrypt areas in the image that could be sensitive or potentially contain personal data. The problem of this kind of method is that we can still retrieve the original data if we have the encryption key, and if that's the case, GDPR still applies, so it wouldn't be useful for our case. And another method which is used in certain CCTV systems is to try to remove completely all the elements in the video frames that could contain personal data. So in this case, every person. But of course, this is not very useful for us because we're actually removing the information that we want to keep. So you might have noticed that all of these methods have something in common, which is that they manipulate or process the original video somehow. The problem of this is that if we want to perform the anonymization process automatically, the detection of these sensitive areas needs to be completely perfect. Because let's say that we are able to detect all faces in a video, like in 100% of the frames in 99% of the frames in a video. So that's quite impressive, but the problem is that if there's even only one video frame where we can still see these people's faces, then anonymity is not ensured. So an example of this is this paper, which was published by researchers at Google, and they said that they are capable of anonymizing 89% of the faces in Google Street View, which is still impressive, but this means that 11% of the faces in Street View are actually completely visible. So not even Google is able, well, at the time of the publication of this paper, to ensure anonymity in Street View. But let's say that we are able to blur 100% of the faces in Street View. Personally, I'd say that, for instance, these people could be recognized even if their faces are blurred, especially if someone knows them. So yeah, what we thought for this project was, instead of following the general approach to manipulate the original video. It was to try to create an alternative video where we only transfer the information that we want to keep without transferring all potentially sensitive or all the personal data. To do this, what we want to do is first detect all the objects that are of interest to us. So in our case, this was all the people and all the vehicles, which shows these vehicle labels. Then the idea is to try to infer the 3D information from the 2D video to estimate where every relevant object is located in the 3D space. So this corresponds to the ground plane. If we know these locations plus the type of object that each object is, we could. Can you hear me? Or? Yes. Okay. Yeah. So if we have this information, we could, for instance, create a 3D animation of the environment where we could use default 3D models for each of the objects, so that this way we can completely guarantee anonymity. So this is the pipeline of the whole method. I'll go through it really briefly because this is kind of overwhelming and not very pretty. But what we basically do is we extract all the frames in the video as image files. Then on one hand, we perform object detection, and we try to infer the distance of every point or pixel in the image to the camera by performing depth estimation. Once we do this, we also perform object tracking so that we can smooth the results. I'll cover it later. And aside from this, we have to perform a process called camera self-calibration that I will also explain a bit later, to gather some parameters that we need to convert all this information to 3D. And once we have these estimated locations, we can then create our anonymized environment. So for this first prototype, we implemented everything in Python. We used TensorFlow and Keras on top of it for all the deep learning models. We used OpenCV for all the image operations, and there are a couple classic machine learning techniques that we had to implement, for which we use scikit-learn, and then let's be NumPy and SciPy for all the multidimensional arrays operations. Okay, so before I go into each of these steps, I would like to show you the demo video that I'm going to be using for to show the results of all of the models. Oops, sorry. Yeah. So it's a video from a very popular benchmark for object tracking algorithms, and it basically shows an outdoor scene in a walkway with several people passing by, entering the frame, leaving the frame, or staying within the frame. Okay, so first we'll delve into the object detection phase. For this, we used an object detector that is quite popular nowadays. It was first released 2 years ago. It's called Mask RCNN. And what it basically does is to propose regions in every image where objects could appear, to then classify the objects within these regions. On top of this, it also performs segmentation, which means that within the box corresponding to a detected object, it is capable of saying which pixels belong to the actual objects and which ones belong to the background. We trained this model on the Microsoft CoCo dataset that I think Callum also mentioned, one of the models he used. It contains 80 different object classes, so only 80 of them have segmentation masks, although the dataset has more classes, from which we adjusted the model so that it only outputs the 6 selected classes by us, so the people and the 5 vehicles. These are some examples from the dataset with the ground truth annotations. And this is another example where we ran our model. So this is a frame from a dataset called Cityscapes, which is pretty popular for training autonomous cars in research. And so here we have the original annotations, and this is the output that we get. So as you can see, it works pretty well for both cars and people, even if the people are far away from the camera. It also works well when the objects are quite occluded, so not only detects them well, but they are correctly segmented. And this is an example from our demo video. So again, we can see that it works really well for people with very high levels of confidence, almost always 100%. And again, with objects that are severely occluded, it still detects them well. This is an additional example I wanted to add because this is a bit of an extreme situation or scenario, which is this frame also from cityscapes, where the lighting conditions are kind of poor. Well, in this screen, it looks actually much nicer, but it's a quite dark image. And still, it performs quite well for all the objects. It also differentiates well between motorbikes and bikes. And it's actually interesting because this is the ground truth, and the authors didn't even annotate these motorbikes, probably because they thought that detectors weren't going to be able to detect them. But in this case, we're actually kind of outperforming the so-called ground truth. So this is pretty impressive. And after this, we go into the next step, which is the depth estimation. So for this, we're using a method called monodepth. And it's a bit different from other depth estimators, because instead of trying to actually predict a depth map for each frame, it's an unsupervised method. So what it does is it tries to predict how the pair image to the input image would look like in a stereo camera, so in a 3D camera. And as you all know, with a 3D camera, so with two cameras, we are able to also capture depth from a scene. So the idea behind this is that if we have these two images, we can compute the disparity map, which is basically says for each point in an image, the distance, the horizontal distance to this same point in the other image. It looks something like this. And then from the disparity map, if we know certain parameters from the cameras, we can compute the depth map by using geometry and triangle similarities. I just added the math so that it look more trustworthy, but I'm not going to go into that because now it's not really time for math. So we can basically get depth from two images. This model was trained on the same dataset that I mentioned before, cityscapes, and it was tested on a subset from a pretty similar dataset also used for autonomous cars called Kitty. And this is an example of the output that we get for one of the frames from our demo video. So as you can see, it's basically the yellower it is, the closer it is to the camera. So as you can see, it seems quite good, especially considering that we just have a 2D image and we have no depth information at all. But at the end of the presentation, I'll go back to this because this is actually kind of like the performance bottleneck in the whole method, but we'll go back to that later. Now we'll go into the object tracking. For this, we use a method called DeepSORT. It's basically like any other traditional tracker. It's based on a paradigm called tracking by detection, which means that you have to input detected objects from all of the frames in a video, and then it associates them across the whole video. So this is quite useful for us because it's actually transparent to the object detection that we use, so we can reuse our detections that we got with mass cars in N. And it basically associates these detections by finding patterns in positions, in speed, etc. But apart from that, it's also pretty cool because it has an additional deep neural network which extracts appearance features. So it's also able to associate detections by their appearance. And this network was trained in a large-scale dataset containing images from people. So this is an example of a fragment from our demo video. And you can see that it works pretty well. So the objects are correctly identified in each of the consecutive frames. And not only that, but also, for instance, you can see here that there's this guy kind of on the back who has been tagged with the ID 4, and then there's a moment where it's completely occluded and we miss it, and then it reappears and it's correctly retagged as 4. This is kind of impressive among object trackers because this is usually where they tend to fail. But the thing is that, as we saw in the previous briefing, the appearance association network was trained only on people, and we are not only interested in people but also in vehicles. So we wanted to see how it would work in a, let's say, like in a road scene. So yeah, you can actually see that vehicles are correctly tracked anyways. There's some problems, like when they reach the borders, the IDs switch sometimes, and there's also some kind of flickering, so sometimes the detections disappear, but then they are correctly tagged afterwards. So yeah, it means that this method was actually useful for what we wanted to build. Then the interesting thing of the tracking is that on one hand, it can help us filter out possible false positive detections, because if, for instance, the tracker is not able to find a specific detected object in any other frame, then it probably means that it's a wrong detection, so we can filter it out. And it's also interesting because, for instance, in the demo video, we saw that this guy disappears and reappears. So in this moment where it's occluded, we wouldn't be able to estimate its location because it's not in the video. But thanks to the tracking, because of the guy being correctly identified, we are able to linearly interpolate its missing positions when we estimate them at the end. Okay, so let's go into the camera self-calibration process. So the thing is that there are certain parameters from the camera that we use to record the video that we need to convert to the information to 3D. So one of these parameters is the focal length. If any of you is into photography, you probably know this concept. And the thing is that this is the same scene, and it has been, the picture has been taken with a shorter focal length and gradually with a higher focal length. So as you can see, even though the scene is the same, the spatial relationships change a lot within the image. So we actually need this parameter to be able to correctly convert our 2D images into 3D. Normally, to get these kind of parameters, we either know them beforehand, or we can, if you have the camera, we can record certain scenes or certain objects so that we can estimate this value. But the thing is that here we are assuming that we have no access to the camera that was used to record the video, and we also don't know which camera it was. So we want to make the method completely transparent to the video that is input. So the idea to do this is that we know that in parallel lines in the real world intersect in images in what we call vanishing points. So normally all of these vanishing points are located in what we also call the horizon line. And images are usually modeled with this kind of perspective where we have horizon line composed by several vanishing points, and then a vertical vanishing point. So the idea to be able to estimate this focal length value is to try to find where these vanishing points are just based on the video that we have. And what we do is we thought about tracking one person in the video throughout the whole sequence, because we know that if this person is we assume that this person is just walking and they are standing straight. So then you know that if a person moves, the line that goes from feet to feet and from head to head, these lines are parallel. So then we know that in the image they would intersect in a vanishing point. And likewise for the vertical line. So if the same person moves, we know that the person is parallel to itself on another frame. So then these lines in the image would also intersect at the vertical vanishing point. Then if we find all of these parameters, we'll see later that we can calibrate the camera. So this is quite useful because we have already performed object detection and tracking. So from the tracking results, we can already choose a person from the video. In our case, we decided to choose the person that appears the most in the video. And then to find the locations of the head and the feet, knowing that we also have the segmentation masks from mask carcinogen, we did this kind of trick where we fitted an ellipse on the mask of the person, and then we intersected the major axis of the ellipse with the bounding box of the objects. So this is better seen in the example video. So then here, these circles indicate the intersection points of the axis. So these are our estimated head and feet locations. So this way, we can get lots of estimates of this kind of head-feet poles. And then we can find the intersection point for each pair of poles. This way, we get a lot of candidate points, and then we perform linear regression to estimate where the horizon line is. And likewise for the vertical vanishing point, which we average among all of the candidate points to find our final estimate. And then knowing these potential vanishing points, we can calculate the focal length. So the guy from this video said that we can calculate it with simple 9th grade geometry. I calculated it like this, so I think I went to the wrong high school, but now it's a bit late to fix that. And then after that, we have the final step, which is scene reconstruction. And the thing is that, okay, we have a 2D video, no depth information at all. We actually cannot really estimate 3D information because for a 2D image, there are infinite solutions of how the 3D environment could look like. But in our case, we have an estimate of the depth or C component of each pixel or each 2D point, and we also have an estimate of the focal length. So we can do, I'll also cover this kind of briefly, but just to show that it's, there's some cool stuff behind. But this is a very, very simplified way of modeling an image, where this would be like the camera sensor, and the origin point would be the lens. This is a real-world point, and this is the projection in the image. So basically, we apply the same principle as in with depth estimation. So we have the depth component, so C, and we also have F, which is the focal length. And by applying triangle similarity, we can get Y and X. But just to show you that it's once we have these two values, it's possible to get an estimation or approximation of all the other coordinates. And then this way we can calculate the 3D coordinates of each 2D point, but we want to get an estimate of where each object is located in the ground plane. So we do this by selecting several points within the object, and then we average their coordinates to get an estimate. We do this so that the possible outliers that we could find on the boundaries of the object, because all of this is background, so there could be some variation, so this way we can make it a bit more robust. Right, so as I mentioned before, we had quite a lot of trouble with the depth estimation. And right now it's what's the main bottleneck in the pipeline. Because, so here we can see the frame that I showed you before. And this model, so it was just trained on cityscapes, gave a kind of a better result than this one, apparently. But this model actually performed much worse in every other kind of scenario aside from our demo video. So the thing is that there was a large variation on the results that we got depending on the model, and also depending on the kind of scene that we had. Because the thing is that this model was trained on this kind of data like cityscapes or kitty. So all of these videos have been taken from a car, and all of them have the same height or the same viewpoint. So if we actually show the model video from a completely different viewpoint, so a higher camera angle, we started getting a lot of weird stuff and a lot of artifacts in the depth map. So for instance, the ground plane, we would expect it to be kind of gradual, but then we start getting like weird things in the background. And so what in the paper looked like it was pretty nice and state-of-the-art. Wasn't really like that. And also, it doesn't take into account the time domain, so for every frame in the video, it just outputs a different depth map. So there's not really consistency within frames. So for instance, these frames are from the same video. And yeah, even the ground floor gets different depth maps in each frame. So this leads us to the kind of final output that we got. So this is a very basic visualization. We just have a 2D grid which represents the ground plane, and each point belongs to an object. These are the classes, so in this case, all of the objects in our video were people. And as you are going to see, the depth estimation gives us a lot of outliers and a lot of flickering. So that's the main problem right now, that we can kind of see which objects are in the scene, where are they moving, kind of. Also, there's a guy there who doesn't move that much, so yeah, he's static. But that's the main problem with the other points, that the depth really varies in the z-axis. And also when objects enter or leave the frame, it also gives some confusion to the model. Then afterwards, once we have this data, we could, for instance, create, as I mentioned before, a 3D environment with default models for each object. As you can see, I wasn't born to be a 3D animator, but I hope that you get the point. And then I realized that the demo video that I used only contains people, because it was a bit hard to find a video with ground truth positions, because no one seems to be doing this kind of stuff. And the only videos that I found were 2 which only contained people. So I also wanted to try it in a different video, such as this one, where we have both people and some vehicles. So here we can see that the people on the crossroad are correctly tracked. Then we can see the cars that are behind. And here we have a track on the background, which is correctly tagged as track. And so here this was just like a frame where this was the only frame where it happened, but I found it kind of funny because so there's this Jeep here, and then it's actually just for a moment confused with a truck. And this might be because we don't really have a label for this kind of car, like a van or something. So sometimes it flickers between car and truck because it's not really sure which type it is. All right, so then once we saw this, we definitely know that the main problem is the depth estimation. So for future work, if we actually know that we would like to anonymize a video after recording it, before we want to anonymize it before we record it, it would be interesting to already record it with a stereo camera or with multiple cameras, because then inferring the depth information is much more straightforward and much more accurate. But if we don't know it beforehand, so if we consider the same problem that we posed for this project, then there's still a lot of things that we could do to try to improve it. So the main thing would be, like usual, to train the model with a larger data set and with more variety. Because here we trained it in data that, again, it just showed kind of the similar viewpoint in every image. So it would be useful to show it images from very different cameras and very different heights and camera angles. Or actually the opposite. So there have been some projects, I think a project from NVIDIA where they did kind of a similar thing, but just for football matches. So then it would also be interesting if you know that you want to use it for, they didn't use it for anonymization just to recreate a football match. But if you know that you want to use it for a very specific scenario, it's also interesting to just train your model with images from that scenario and completely overfit it for it, but then you know that it will work just there, but it will work better. There are also some other things that we can do. So for instance, for the object tracking, we could use a different paradigm that appeared recently, which is tracking by segmentation instead of tracking by detection. In this case, we could do it because we are performing object segmentation as well. And then if we are using multiple cameras or a stereo camera, we could also do 3D tracking, which is already performing tracking on the ground plane. So that was it from me. And if anyone is interested in any of the techniques that I showed, or the whole method, or you would like to try any of them, or try to implement this kind of method, or any other kind of anonymization method, I've pasted all the links to the papers and the official implementations here. So yeah, that's basically it. And if you have any questions, you can tell.